Okay, this is section 7.4. We're looking at page 402 in your textbook. We're reasoning about triangle and quadrilateral properties. All right, so there's a few things that, it's quite a long lesson in regards to the board work I had to put up, but there's a few facts that we need to know from today's lesson that you need to be familiar with moving forward. You don't want to have to try and prove these every time, so you're going to have to be familiar with them. First, a few definitions. There's 3 definitions in this section of the textbook. First one is a mid-segment. It's a line segment connecting the midpoints of 2 adjacent sides of a polygon. All right, so what that means is, if this is our polygon here, we see a square. It connects the midpoint of one side to the midpoint of another side. So that's referred to as a mid-segment. Okay, so if I wanted to look at a different shape, if we looked at a triangle, for instance, our mid-segment would be from one midpoint to another midpoint. Okay, so that is a mid-segment. Okay, we have a trapezoid. Again, from one mid-segment to another. Sorry, from one midpoint to another. So, whenever we're talking about midpoints, we know each line on either side of that midpoint is equal. Okay? Each side. Okay? These dashed lines, you'll see 1 dashed line, 2 dashed line, as up to even 3 dashed lines, which you see over here. Okay? Anybody know the difference or why you see that? 1, 2, 3, Santos.
To see which ones are equal?
Right, so when we look at this particular shape, these 2 are equal because they have 1 dash. The reason why we use 2 dashes is because if I use a single dash here, I'm saying that this side is equal to this side, and that's not necessarily true. Okay? So as we increase through different lengths, we may go up to even 4 dashed lines if we need to represent 4 equalities in the shape. Okay? You always start with 1 dash, and then if you need a second dash, then you'll go to 2 dashes. Okay, so that's a mid-segment, from one midpoint to another. You can tell me what a midpoint is. Matthew.
The middle of a mid-segment?
Right, well, not the middle of the mid-segment, but the middle of a line. That's a midpoint. Okay, just in general. And a mid-segment connects 2 midpoints. Okay, so very important. Obviously, to know what a mid-segment is, you need to know what a midpoint is. So that's important that we understand that. The counterexample is an example that proves that a hypothesis or conjecture is false. So in other words, the counterexample is an example that is opposite to what we made a conjecture about. Okay, so if I say in the last test we had, I think it was a measure of heart rate versus temperature. If I say that, my conjecture is heart rate is increased as temperature increases, but then I look at one example and I see a very low temperature and a very high heart rate, that would be a counterexample. Whatever is the opposite of the conjecture would be referred to as a counterexample. Okay, yeah.
So essentially, it's like just like it's a basic example. Somebody said if you put a glass of water upside down, the water won't spill out, and then you actually do it and it does come out.
Yeah, that would be a counterexample. Good. Yeah.
Sir, conjecture is a guess, right?
Conjecture is a guess or a hypothesis. Yeah. It's a little better than a guess because a guess typically is not based on any data, whereas a conjecture is based on some data. Okay, typically you're making a conjecture based on some sort of evidence. All right, median. Final definition in this section is the line drawn from a vertex of a triangle to the midpoint of the opposite side. Who can tell me what a vertex is? Yeah, Michael.
It's the corner of the shape.
Right, exactly. It's a corner of a shape. That's one good way to put it. So in this case, we have 3 vertexes. Okay, we have vertex A, which is this corner, vertex B here, and vertex C. We have a rectangle. We can have 4 vertexes. Okay, so when we're talking about a median, it's a line drawn from a vertex of a triangle to the midpoint of the opposite side. So from a vertex to to the midpoint. So that means these two sides are equal. So this would be median A. Okay? This would be median C. So from vertex C to the midpoint of the opposing side. Okay, we can do that for any shape triangle if we want to give a little bit of a stranger shape. A little too strange. Okay, so ABC, if we want to draw median B, okay, I'm going to find the midpoint of the opposing side, so the middle of here, and then I'm going to draw from vertex B to the midpoint, okay, where these two sides are equal. All right? Median C, I would go from the vertex C to the opposing midpoint, okay? Yeah.
That was a rectangle.
From a rectangle, no, it's only with a triangle by definition. Okay? Median is by triangle. Yep.
So isn't a median like the middle number of a set of data?
Yeah, that's also in statistics. Yeah. So there's two different definitions, one for geometry, one for statistics. Okay? All right, so the first example, we have a conjecture, a shape formed by mid-segments form the same shape. So what that means, what I'm referring to here is the same shape. I'm saying that when we join the midpoints of the exterior shape, the conjecture is that the interior shape is the same as the exterior. So if I have a trapezoid here in white, the conjecture is saying that if I join the midpoints, the midpoints, so creating mid-segments, then I'll get a trapezoid on the interior of the shape. Okay, that's the conjecture. So as we can see, if I go ahead and join these midpoints, I'm joining all my mid-segments here, what you notice is that the shape inside is actually not a trapezoid. All right? So this would be a counterexample. So the yellow shape is a rhombus. Who can tell me what a rhombus is? Yeah, Carlos.
Diamond?
No, not necessarily. Yeah.
Parallelogram?
It can be. There's a better definition, Dan.
Quadrilateral?
Okay, can be, yes, but there's a better definition of a rhombus. Nobody? Matt?
Parallel.
Michael, sorry?
Parallelogram?
You just said that. Josh.
Polygon.
Okay. Yes, Andre.
All sides are equal, but they are not perpendicular to each other.
All sides are equal. Is there a stipulation that they can't be perpendicular to each other? Mark?
A kite.
Okay. Could be. Yes?
A mixture of a square and a parallelogram?
No? Michael?
All sides are equal, but the angles are different?
Yes, well, just the definition of a rhombus is all sides are equal. Right? So a square technically is a rhombus with right angles. Okay, so good, Andrea. So basically all sides are equal. So in this case then 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So that's a rhombus on the inside. Okay? So the conjecture was that I would get if I joined the midpoints on the interior of a trapezoid, I would also get a trapezoid. That's not the case. I get a rhombus. Yes, Dan.
So wouldn't those two lines on the other side have one tick too, since it's cut in half?
Sure. Any question there? So that gives me a counterexample, therefore the conjecture is false. Yeah.
What if you're doing mid-segments of a diamond or a rhombus?
Yeah, we're going to see that as we go. Yeah. Oh, so 1b, okay. The conjecture now is that all interior shapes formed by mid-segments are parallelograms. Who can tell me what a definition of a parallelogram is? Chris.
When all the sides are parallel to each other.
Good. So there's two sets of parallel sides. So the opposing sides are parallel. All right. So that's a parallelogram. So we're saying that the interior shapes formed by joining the mid-segments, which are here, form a parallelogram. So we can see no matter how strange the shape I create, you can see the inside shape always is a parallelogram. Okay. In the case where it doesn't appear to be, this might not be parallel to this, it doesn't really appear, you can see that my midpoint is actually a little bit off here. this side is much shorter, so that point should actually be over here. Okay, which gives us a better looking parallelogram. Okay, Matthew.
What about a three-sided shape? Would it still be
A three-sided shape?
yeah, these are all straight.
Okay, let's see. Okay, obviously if we join the mid segments of a triangle, we don't create a parallelogram because we create another triangle. Alright, so no matter what the triangle looks like,
So wouldn't the first conjecture be right? Well, for triangles.
the first conjecture for triangles
Yes.
would be correct, yeah? So the same shape, if you join the mid segments of a triangle, you also get a triangle, yeah. But here we're talking about, quadrilaterals. And I think, sorry, that was in the textbook, I just shortened the conjecture. Let's see. Yeah, it does say quadrilateral. The shape formed by mid-segments of a quadrilateral has the same shape as the original quadrilateral. So this is referring to quadrilaterals. This is also referring to quadrilaterals. Good question, though. Okay? Yeah. All right, so in this case, the conjecture is true. So all interior shapes are parallelograms, therefore the conjecture is true. And we should test more samples to be sure. So even though you might get one example that shows us that the interior shape is a parallelogram, doesn't mean it's true. You have to test multiple shapes. Okay? So that's important to note. Although you could get one example that proves your conjecture, it doesn't mean you're true. You have to prove multiple examples. However, if you get one counterexample, do you need additional counterexamples to disprove your conjecture? No, because as soon as you have one counterexample, you know it's false. Okay? So multiple examples, one counterexample needed to disprove. All right, example 2. The conjecture says the median through the third angle is an isosceles triangle is never perpendicular to the base. So what I mean by the third angle here is I'm talking about in an isosceles triangle, we know that we have two sides that are equal, and we know we have two angles that are equal, x. Okay, no matter how you draw, however that isosceles triangle looks, these two angles are going to be the same, and those two sides will be the same. Okay, so when I say a median through the third angle in an isosceles triangle, what I'm referring to is the angle that's not in common with another angle. Okay, so in this particular case, I'm referring to this angle, or this angle. Okay, that's what the conjecture is referring to. Any questions about that? All right, I want to make sure that is clear. So the median, remember we know what a median is. It's from one vertex to the midpoint of the opposite side. Okay, we learned that by definition at the beginning. So if this is vertex A, B, C, I go from vertex A down to the midpoint of the opposite side. Okay, these are double lines. Okay, the conjecture says is never perpendicular to the base. Well, we can see here if I were to draw this exactly to scale, we get a line that is actually perpendicular to the base. Okay, so the example that I've shown is exactly the opposite of the conjecture. So this would be a counterexample. And what you end up finding is no matter how you draw that isosceles triangle, if you split the third angle in half, you always have a median that's perpendicular to the base. Okay? So that is something that you need to know. That's a fact.
Shouldn't you
All right.
get more examples?
Yeah, we can draw more examples, but in each case it's going to be the same. There's more examples.
Is that just for triangles?
Yes. Yeah.
Oh.
Okay. And there's more examples in the textbook. So we can see from the diagram that the median is perpendicular to the base. Therefore, it's a counterexample. And conjecture is false. All right, example number 3. The conjecture says the sum of the exterior angle and two opposite interior angles is 180. All right, so I've tried to show a few examples. Again, there's more examples in the textbook, but let's look at the first example here in yellow. So the sum, it says the sum of an exterior angle, so the sum of this angle and two opposite interior angles. So when we're talking about opposite interior angles, we're not talking about the supplementary angle of the exterior angle. We're talking about these two. So opposite of that exterior angle. Okay, I hope that's not confusing. I don't want you guys to think when I say opposite, I'm referring to this angle. No, I'm referring to the sum of these two. So what the conjecture reads is that the sum of the exterior angles, so this angle, plus these two angles is equal to 180. So if I do that here, I have a 90 degree triangle. I have 90 degrees plus 45 plus 45. I get 180. So you might be tempted to say, yes, that's true. My conjecture works. Okay? In this particular angle, in this particular example, it does work. Okay? But I'm going to test this conjecture with another angle, another exterior angle. All right? So just using the same triangle, I know if this is 45 degrees, we know that this whole line is 180. So this angle here, this exterior angle is going to be 135. Any questions there about that? Once I know that this exterior angle is 135, the conjecture reads that 135 plus the two opposite angles has to equal 180. So 135 plus 90 plus 45 is not equal to 180. Okay? So therefore, the conjecture is not true. Okay? The conjecture is false. So this would be a counterexample. Okay? Looking at another triangle, not that I would need another example because I already have one to disprove it, but just to look at another example, again, this angle is going to be 120 because I have 180 minus 60. So 120 plus 60 and 60 is equal to 240. So again, this is disproving my conjecture. Okay? The reason I showed 2 is because there is a relationship between the exterior angle and the two opposite interior angles. Anybody know what it is? Yeah, Andre?
The exterior angle is equal to the two opposite interior angles.
Excellent, yeah. This is a fact you need to know. Okay, and I'm taking Andrea's word for it, but let's prove it now. So this angle we're going to look at this scenario here. We have 90 degrees, and I'm saying that's going to be equal to the sum of the two opposite interior angles. 45 plus 45. Okay, so that one works. Let's check this one. So I have here 135 degrees is going to be equal to the two interior angles. Okay, that one works. Let's check this example. So I have 120 degrees is going to be equal to the sum of the two interior angles. This one works. Okay? Any questions there? So that's a fact now. We need to memorize that fact.
Why wouldn't you use 45, 45?
Sorry?
Why wouldn't you use 45, 45 again?
It's just the triangle that I drew.
No, like to figure out if it's if that statement is true. For the 135. The 135 angle.
This angle?
Yeah, how do you know it's because can't you add 45, 45 and you would say it's 90, so it's wrong?
No, because it's the opposite two interior angles, not the one here.
Oh.
It's these two. If you're looking at this exterior angle, it's these two. Yeah, so it's away from it, not the supplementary angle. All right, last example. So the conjecture says a mid-segment of a triangle is half as long as its opposite side. So what am I talking about here? A mid-segment of a triangle. So in this case, this is a mid-segment. Remember, connecting two midpoints, this is a mid-segment. So I'm saying that this is half as long as its opposite side. So its opposite side would be here. This would be its opposite side. So if I'm saying that's a half, this is 1. Okay? And they actually use geometry software to prove this. but to give you the Coles note, it's true. Okay? So your mid-segment is always half of your opposite side. Noah?
I have a question about the other part.
Yeah, this one?
So does that just work with triangles where the two opposite interior angles equal the exterior?
Yes.
So it doesn't work with anything with more than three sides?
No. Okay? Because there's too many sides to consider in that case. It's only with triangles. All right, so we're talking about mid-segments. Mid-segment is two midpoints joined together. The mid-segment is always half the length of the opposite side of that mid-segment. So if we're looking at this triangle, we're looking at mid-segment ED. ED is going to be half the length of AB. And this is important, guys. You're going to need this on your EQAO. You're going to need to know this information as a fact. Okay? So in this particular case, let's say GH, or let's just say KI is equal to 2. All right? KI is equal to 2. These are mid-segments. I could ask you, what's the length of LJ? Okay, you should be able to know this now based on the fact that we know the mid-segment is half the length of the opposite side. So what is the length of LJ? Mark?
2.
2, very good. And the reason he got that is because he knows that this is 2 and this is 2 because that's the midpoint. So this length is 4. Half of 4 is 2. Okay, that's the type of questions you're going to see. Any questions there? All right. Same thing would be KJ would be half the length of GH. And you can see, even based on this rough sketch, it's pretty accurate. That looks about half of that. Okay? All right, so finally, in summary, there's a big chart on page 407. Please also make sure you copy that down for homework. I didn't have time to write it on the board, but it's an important chart. It goes over what mid-segments of different shapes give you for the interior shape. Okay, you're going to be responsible for that. So, for instance, a mid-segments form a rectangle. If you have a kite, if you join the mid-segments, you're going to get a rectangle. If you have a isosceles trapezoid, you join the mid-segments, you're going to get a rhombus. What's a rhombus again, Selvin?
A rhombus is where a shape where all four sides are equal.
Excellent. That's right. Okay, so in summary, examples can support a conjecture but don't prove it. You need multiple examples to prove it. You only need one counterexample to disprove a conjecture. The mid-segments of any quadrilateral form a parallelogram. That's been proven. Okay? So if we join the mid-segments of any four-sided shape, we're going to get a parallelogram. Median through third angle of isosceles triangles perpendicular to the third side. We saw that in example 2. The exterior angle of a vertex equals the sum of the two opposite interior angles. That was this example right here. Example 3. And the length of a midsegment in a triangle equals half the length of the opposite side. Again, another fact that you need to have memorized. Okay, you don't want to have to try and prove this every time you go through a question like this. It just has to be given information. Any questions? Yes.
So does that theory work for quadrilaterals too?
This? No. It's only for triangles.
Okay.
Okay? All right. That's the end of the lesson.